Hello and welcome to my presentation. This presentation will be about fluids, and we will talk about the measurement of pressure and flow rate, hemodynamics, velocity and pressure in blood vessels, as well as the role of viscoelastic properties of blood vessels in circulation. So we will first start with the measurement of pressure and flow rate. So first, what is pressure? Pressure is defined as the amount of force that is exerted per area, and it is usually caused by the gravity or acceleration, and you can calculate the pressure by using the given formula, where the pressure is defined by the force divided by the area. If we now have a closer look on the fluid pressure, then we first have to emphasize that fluids do not have a definite shape. So the pressure in fluids applies in all directions, as you can see here in the picture. And in fluids, the force that is exerted on a certain area equals the weight. And the weight is determined by the amount of fluid that is above the object. And so we can conclude that pressure increases vertically downward since the amount of fluid, and so the weight, increases. But the pressure is constant on the horizontal axis since there is no change in the amount of fluid. So if we now want to calculate the pressure in fluids, we first have to substitute the force with the mass multiplied by the gravity, which defines the weight that equals the force. And we can replace the mass by using the formula for density and solve the equation according to the mass. And then we get this equation that defines the pressure in fluids, which is the measurement of force exerted per area on an object in a fluid. The flow rate is a measurement of the volume that passes through an area per time, and this can be calculated by the given formula, where Q is defined by the volume divided by the time. It is important to mention that liquids are incompressible. That means that you cannot fully squeeze a filled water bottle, no matter how hard you try. And therefore, we can say that liquids maintain the volume that flows in and out. So Q is constant. And the important factor is the cross-section area, since the flow rate depends on it, but we will see in a minute. So this formula can also be continued. We can first substitute Q with the volume divided by the time. And the volume can be replaced by the area multiplied by the diameter or the width of fluid. And this results in the area multiplied by the speed of the fluid, since the speed is defined by the diameter divided by the time. And if we now refer this to our equation, this is known as the equation of continuity. And you can see it here in the picture. This is what is meant with maintaining the in and outflowing volume of fluid. The bigger the area, the less is the speed of flow, and vice versa. So in order to compensate the smaller area and the higher velocity or speed of the flow on the other side. So let's move on to the next topic, which is hemodynamics. Hemodynamics describes the dynamics of blood flow, which includes the circulatory system and incorporates physical laws within the blood vessels. And here are some hemodynamic parameters, for example, the heart rate and the blood pressure. The velocity and pressure in blood vessels. Here we have 5 types of blood vessels in our body that take part in the circulatory system and participate in the blood transport. And in these vessels, there is a certain blood pressure, and the 5 types are the arteries, arterioles, veins, venules, and the capillaries. And the blood flow describes the movement of blood through the vessels. The direction of blood flow you can see here. The blood flows through the arteries, through the capillaries, and then to the veins. And there is an opposing force, which is the resistance to flow, and this depends on the vessel diameter. And here in this given picture, you can see what is meant by that. So if the diameter increases, which is the case here in those areas, the resistance to flow and the velocity or the speed of the flow decreases, whereas if the diameter increases, the resistance and the speed of flow also increases. And the blood flow can be described or calculated by the Poiseuille's law, which you can see here in the picture, but I will explain it on this example. So we assume that we have the same pressure gradient in both of the vessels, and in vessel 2 we have the radius, which is 2 times of that of vessel 1. And therefore, by using the equation of the Poiseuille's law, the resistance results in being only 1/16 of that of vessel 1, whereas the flow is 16 times that of vessel 1. So this justifies this relationship, which we already have explained. And now the velocity. The velocity describes the rate of blood flow, which varies inversely with the cross-section, which is nicely shown in this diagram. As you can see, the diameter increases from the arteries to the arterioles, having its peak in the capillaries and then decreases in the direction of the veins. And if we now look at the velocity, we can see that it is the same, but in the negative direction. And so we can assume that the relationship here is inversely proportional. And this is also shown in this relationship. So now the pressure in blood vessels describes the force that the blood exerts against the vessel walls, which is measured in milliliter of mercury. And it is generated by the heartbeat, where we differentiate two kinds of pressures. The first one is the systolic pressure, which is generated by the ventricular contraction. And the second one is the diastolic pressure, which is generated by the cardiac relaxation. And here are some average numbers in the human organism, where we have 120 milliliter per mercury of mercury for the diastolic and 80 milliliter of mercury for the diastolic. We have different factors that affect the blood pressure, such as the blood volume, blood viscosity, cardiac output, and the resistance. And those are all in a proportional relationship. And as you can see here in the diagram, the pressure decreases from the in the direction from the aorta to the veins. And lastly, we will talk about the role of viscosity or viscoelastic properties of blood vessels in circulation. First, what does viscoelasticity mean? Viscoelasticity describes a material that has viscous and elastic properties during deformation. And there we have the viscosity. The viscosity is a measure of resistance to flow. And here, for example, you can see that, that we have water. Water, for example, is relatively thin and therefore has a low viscosity. And in comparison to that, we have another substance that would have a higher viscosity. And elasticity is the ability to return to its original form after deformation. An example for that would be shown here. So we can conclude that blood vessels have viscoelastic properties, but why is this important? The importance in human body is relatively big during the circulation. Um, the viscoelasticity allows to withstand big amounts of mechanical stress that is, for example, generated by the heartbeat, and to reduce strain caused by the stress. And as we have discussed, there are multiple factors that would cause stress in the human body, and therefore the viscoelasticity of blood vessels has a huge impact on our mechanism. And the importance can be furtherly emphasized if we think about why blood vessels are viscoelastic and not pure elastic. And the answer for that is that it reduces the magnitudes and temporal variations of stress and strain, since it provides a certain resistance in itself, and it reduces the radial wall movement. And taking all those aspects into consideration, the viscoelasticity turns out to be beneficial for the endurance of the blood vessels in our organism. And that's it for my presentation, and thank you for attention.